Hi, everybody. Welcome back to the Chico Math Practice Lab. And in this video, we will continue the unit limits, continuity, and differentiability. And we're going to do the practice set number 3. In this practice set, we're going to take a look at what is a removable discontinuity. What that means here, okay? So here are the here are the 3 problems we're going to practice. And so we said, we said when we give a number a equal to, for example, 1, 2, or pi, to see if f there is a removable discontinuities here. If it is, then we need to find the functions here, right? So which will agree with the f and is continuous at the specific numbers here. Okay, so this video will be a quick and easy video, and so right now it is good for you to pause the video and try to do the problems by yourself, and then come back. We can check the answers against each other. Okay, now go ahead, pause the video and try to do these problems. And I'm going to the whiteboard, and I will see you later. Yeah, I will talk to you later. Okay. Okay, I'm in the whiteboard. And are you ready to work on this set? What is the removable discontinuity? Like always, let's do a quick review, and then I think that will help us to do this practice set. Okay, so when we first start the talk about a function is continuous or not, we start with the limits, right? So like we did before, we said, okay, for a limit here, we have several situations here. So well, maybe I use different color will be better. Okay, so that will be the one. Okay, so we talk about the several situations. So let's see here. So if I have a function like this, right? So if this is my value a, so we say this function obviously is discontinuous at the x equal to a, and so this is this is not a continuous function. Okay, so let's take a look at the other one we also talk about here. Okay, so for these ones here, we have some functions. Like for example, we have a function like this and this. Then we have a jump here. We have like values here. So this is my x equal to a. So obviously from this function here, we know this is not a continuous. They have a discontinuity points there. All right. Okay, now and we also talk about the third situations here. Okay, so for these ones here, let's take a look. And if my function go like this, right? So if this is my function and this is my a values here, so for the first two, the limits exist, right? So for this one, the limit, the third one, so this is the number 1, number 2, and the number 3. So we know the third one limits not exist because you approach from the left-hand side, you approach from the right-hand side, they have different values. So the both number 1 and number 2, the limit exists, but it's obviously, yes, what is discontinuous. Okay, so for the functions, look like the number 1 and the number 2, these two situations, we know at the A, we have discontinuity points, right? So for both this situation, the discontinuity point we call it is removable discontinuity, so this point is a removable discontinuity. It's kind of like it's kind of like the holes concept in the algebras, right? And then for this ones here, this type of the continuity, the number 3, we call that this is a jump discontinuity. Okay, and so the discontinuity is like you have a point, have a it's not a continuous layer, but you'll be able to redefine the functions, right? So you'll be able to redefine a function at that function's, okay? So you can redefine the function, then that function will be continuous at every point. And so that's why you say you can redefine the function at x equal to a, and then that function will be continuous at every point here, right? Okay, now let's take a look. Okay, so now maybe this still is not very clear for you. So let's take a look at our examples here, all right? So the first problem here, this is a part A, okay? So the part A, I have f of x is equal to x4 minus 1, and this is x minus 1 when a is equal to 1. Obviously, for the function, the domain of the function f of x, 1 is not in the domain. So I know the f of x is not defined in the domains, right? Because the domain cannot be included 1, because if you included 1 domain, the whole function, the denominator will become to 0 here. Okay, so now let's take a look here, right? So I said, let's see, so limit x approach to 1 from the right-hand side, f of x. Okay, so this will be limit x approach to the right-hand side. So this is x4 minus 1. This is x minus 1. So if you put a 1 in there, what you will have here? You will have a 0 over 0. Then we say, oh, that's not going to work. So that's why I need to do some manipulations for these functions. So I will say, okay, I can factor this. So x4, I can factor to the x squared plus 1 and the x squared minus 1. Then this is x minus 1, right? Then I can continue to factor it. So this is x minus 1. This is x squared plus 1. So what is here? This is x minus 1, x plus 1. So far, so good? Okay, so now the x minus 1, x minus 1, you cancel out. So what is here? So here you will have is what is 1 plus 1 times 1 plus 1. So you will have 4 here, right? Limit is 1 plus 1 times, okay. So the same thing is here. If you do limit x approach to 1 from the left-hand side, f of x, so this will be what? This will be the limit x approach to 1 from the left-hand side. So this is x4 minus 1. This is x minus 1. So it's the same thing. It's, so it's the same thing. It will be what? Will be 0 over 0. So this one here is the same. You can factor, and then you can cancel the trouble terms. So this trouble terms here is x, right? X minus 1. So it's equal to 4. So this one's here is 4. This one's here is 4. So limit exists, but function value is not defined here, right? So I know this one's here. So what is type of so this is a removable. So this is a removable discontinuity. Okay, so what that means is removable. That means if I give a specific definition at x equal to 1, so this is x4 minus 1, x minus 1, right? So we already know after factor, you will factor to this is x plus 1, x minus 1, x plus 1, and the x minus 1, right? So it cancel out. So this one, you can find that this is x squared plus 1, and this is x plus 1, right? So this is, you can do everything here when the x is not equal to 1, right? So if you foiled it, so this will be x cubed plus x squared plus x plus 1, all right? So for x is not equal to 1, right? So that's why you can define the function gx is x cubed plus x2 plus x plus 1, okay? So this one's here. So I know the gx is here, right? So gx is agrees with f of x, right? When the, for the x not equal to 1, okay, and is continuous. And on the all real number lines, right? That's how we find it. That's what we means the removable discontinuities here. That means, for the a equal to 1, for all the value not, you can define, right? So for the x not equal to 1, you can find the functions here. This function agree with f of x, and it's continuous on the whole real number. Then we say, hey, that's why this discontinuity is recorded as removable discontinuity. Okay, so if you're not clear, let's try to take a look at another example. That is the problem part B. Okay, so the part B, the f of x here is equal to, this is x cubed minus x squared minus 2x. And this is x minus 2 here. So this is we are looking for is a is equal to 2. So obviously, if you see the a equal to 2, and then 2 is not in the domain of this function, because the denominator cannot be equal to 0. So this is not the domain of these functions here. But for here, if we do the same thing, so if you say the limit x approach to 2 from the right-hand side of the f of x, so this is limit x approach to 2 from the right-hand side. If you plug in the 2, what you will get here? You will get a 0 over zeros, right? So in order to find the limit, you need to do some manipulations, and hopefully you can cancel the trouble term. So I will, factor the x out. So this is x minus 2. So this will be limit x approach to 2 from the right-hand side. This is x minus 2, this is x minus 2, x plus 1. Did you see that? Yes, you see that this one, we can cancel that out. So the limit here is what? It's 2 times 2, 2 times 2 times, 2 times 3, so it's 6, right? Okay, so now the limit x approach to 2 from the left-hand side, let's see what we have. So it's the same thing, the limit from the left-hand side, then this is x cubed minus x squared minus 2x, x minus 2. So it's the same thing, you will get a 0 over zeros, right? And now you can do the same thing, you factor that out and cancel the trouble terms here. So this is your factor. All right, so that you factor here, then what you have here, so is 6 again. So in here, when the limit exists, right? And but the function is not defined here. Okay, so now in here we know the f of x is here is so it's x minus 2, x plus 1 over x minus 2. This is when the x is not equal to 2. And then you can cancel this one. And so this one's here when x not equal to 2, right? So this is x plus 1 or you can write this is x squared plus x here, right? So this is where x is not equal to 2. So that's why you can define the function gx here. Gx is x squared plus x here, right? So gx here, so the same way we say gx agree with f of x, right? So gx agree with f of x for all the value x is not equal to 2 and is continuous on the everywhere, right? It's R. So, so the x equal to 2, what type of the, so this is removable discontinuity. Right, so this is a removable discontinuity. That's why, okay, so that's how do we find the removable discontinuities here. That means you can define the specific functions, when the f of x is not continuous at that point, and then that function, this is what the problem asks you, the g functions, right? So then the g function is continuous everywhere in the domains, right? Not in the domain, everywhere, in here is in the real number line. Okay, so now let's take a look at the last ones here. We did dealing with this function before, right? So this is f of x is equal to right. So I hope if you still remember, this is we said it's a sine functions, and these notations here. If you don't remember, probably you can go back to review our limit when we did some practice. So this function we call this greatest integer functions. That means any numbers inside here will come out with a whole number. And this whole number is the greatest number less than whatever this value is, right? So if you don't remember, you might want to review that. Okay, so now let's take a look here. This one here is a limit. Let's take a look at x approach to pi from the left-hand side, right? So this is f of x. So this is a limit x approach to the pi from the left-hand side. And this is the greatest integer function, sine x here. Okay, remember, this is what is the sine functions here, right? So, and this is what? This is a pi. All right, so if you approach to the sine from the left-hand side, that means you approach to from here. So all the value inside the sine, what type of the number you will have here? You will have negative numbers, right? So it's negative 0.1, negative 0.2. So it will be very, very close to 0. But we know the negative number, what is the largest whole number, is less than that number. So this one will be what? Will be negative 1s here. Clear? Okay, so then the next ones here, this is x approach to pi from the right-hand side, f of x. So this means the limit x approach to pi on the right-hand side, this greatest integer function, sine x here. That means I'm approaching from here. If you're approaching from here, all the values inside, in here, right? So all the value inside in here is going to be some positive pointer, some numbers here, right? So now, based on this definition, we know this is the greatest integer function. So this will be positive pointer something. So I know what is here. This is zeros here, right? Okay, so now negative 1 and the 0, they are what? They are not equal to, right? So they are not equal to each other. So we know the limit x approach to pi f of x. So this is not exist. Okay, so this is not exist. In fact, the function going to looks like this, right? So from this is pi, all right? So this is the pi. So when the x approach to, so for everything, you know, like in here, you're going to have a what? So when the, so from pi, so you're going to have a zeros here, right? So you're going to have a zeros here. And so in here, okay, let's do this. All right, so here you're going to have a, so it's okay, so this one's here. So this is a pi, and then this is a pi over 2. So basically, what is your functions going to looks like? It will be like some jumping functions, right? Like we did it before. So this will be like a jumping functions here, and then here, right? So it's going to be like a jump functions here. So this is a jump discontinuities here, right? Okay, so now, okay, so that's what okay, so here, so that's why we say this one's here. So when x equal to pi, we have this is what is a jump, right? So it's a jump discontinuity. Okay, so I'm sorry here, this one's here, this cannot be because everything, okay, greater than pi over 2, so it's 1. Pi over 2 is 1, so this one's here is going to be, so this one's a jump here, so when the pi over 2, so it will be, so it will become 0 again, right? So here. Okay, so that's what this function going to looks like, right? Okay, so then the other function go like this, right? So it's a -1. So here, right? So yeah, like that. All right. All right. So but anyway, so this function is here. This is not removable. This is a jump discontinuities here. Okay. So let's kind of the review that here. So make sure the removable discontinuity is, that means you can, you know, find different functions, and you can find the different functions, and then that different functions is not equal to the when the discontinuity point, but then after you define a new function, and then that function will be able to, is disagree with your functions at that discontinuity point, but it's going to be continuous over the whole real number. That's what it means, the removable discontinuity. I hope that this clarify the concept about the discontinuity. And if you like this video, and you know, feel free to subscribe to it, or if you have questions, and send me a comment, and I will be glad to answer your questions here. Okay, so that's it. And I guess I will talk to you in our next, you know, in our next video, and we're going to talk about how to find the derivative by using the limits definitions. Okay, let's talk to you. Bye.